Okay, so we are now on to the portion of our schedule with general discussion. So the first thing that I'll do is just open up the floor to questions for any of the speakers. We've heard three really interesting but very different topics today. So I'll leave it to you all. And Renzo, do you have a question?
I think Lavinia has one. Yeah.
Yes, thank you. Hi, Renzo.
Perfect.
So Renzo, I think we have a person in common, Martin Krombichler. He was my PhD supervisor. And I saw, I think last year that you guys managed to get some layer fMRI done on a 3 Tesla, which I know he had been working on before I left. I'm now in the US. So I was wondering how feasible really is it, and so supposing I would like to do something like that on a 3 Tesla here, how would I go about that? And is it worth it, or should I just ask for a bigger magnet?
If this is a question to me, I think it's a great topic and the direction of questions that I think it touches the clinical applications. Specifically, the best field strength is the field strength that you have. So if you just have 3 Teslas being guided by 7 Tesla results, as we have seen them, you can do a lot of things. You need to average longer, which might be a challenge in like these clinical applications. Overall, I think there are maybe 8% of all the 260 layer fMRI papers out there now use 3 Tesla. So it can be done. And there's enough signal if you kind of pool a lot of voxels of an entire area together. Maybe to give this question to the speakers, you showed all kind of like very promising and cool results. There seems to be still a gap in making layer fMRI useful for kind of clinical research, in the sense that there are like a dozen or so review papers that focus on the benefits of layer-dependent fMRI for clinical research, but there's very little empirical data. So following Lavinia's question of field strength, what are the kind of practical limits in these kind of clinical research? I know that for clinical day-to-day routine, you need to be much shorter, which we can't be in layer-dependent fMRI anyway. Maybe there's motion. So what is holding us back? Specifically, maybe Joost, you mentioned that we need to validate layer-dependent fMRI in order to kind of to make it a useful tool with your nice temperature example there. And which is still something that the field is figuring out, and we are tuning the sequences. And ultimately, conventional bold is still not well understood, right? Neurovascular coupling is still a thing that we are investigating. So what are the things that we need to practically change to make layer fMRI useful in those clinical? Is it scan time? Is it motion? Is it what is holding us back? Is it field strength?
So I was tempted to immediately shout funding. Like if the Wellcome Trust gives me a bloody grant, I'll be testing people with psychosis. But lo and behold, but more practically speaking, when you talk about the importance of validating paradigms before we implement them in people with clinical disorders, I think it's important, I think, to have a paradigm which you kind of understand in the context of your own imaging, I suppose. And in our instance, for example, with our particular paradigm, we have found a couple of times that we can decode expectations from a particular layer. Now, this is with our particular sequences, with our paradigms. Hopefully, it generalizes to other studies. But I think, you can at least use this to then study perceptual expectations in people with psychosis in that very, small kind of area of application. And when I think about the relationship between the people pushing the methods like you and the people trying to use the methods, I'm not sure whether anybody does rock climbing. I actually don't do any rock climbing, but I think it's a useful metaphor. What you do when there's 2 people climbing a mountain, there's one person going ahead and they put pins in the wall and they try to secure the rope so that the person below them can climb up. The person who's securing the ropes doesn't have to reach the peak of the mountain yet. It just has to pave the way. And I think that's how I'm kind of looking at it. I don't think we have to have figured everything out before we can make it clinically useful. I hope that kind of makes sense.
I have just one comment also. I mean, to the question of what is the major factor. So, I mean, we have also in the study I presented, we also ran 0.7 millimeter. This is actually on structure, not on function. On function, we didn't play around so much here. But from the functional side, it was the way that when we used the 0.7 millimeter resolution that we also acquired for most of them, we could not find this dissociation, for instance, between the input and the output layer in S1. So we could still find the dissociation between superficial and middle. So in principle, the marker we had, this could still be detectable with 0.7 millimeter, but not the boundary between middle and deep. So there was apparently the limitation was in that case really the spatial resolution. So it was much more blurred out. So that this derivative peak was in principle gone for this resolution. So yeah, I guess resolution is a factor, but I guess I don't have to explain it to this audience, right?
Yeah, that's a very good point.
Maybe one comment, Tyler. Sorry, if you want to say something, did I interrupt you?
No, go ahead, Luca.
Maybe one comment, and Renz and I have been talking about this for a long time, and piggyback on what like Esther just said, and also used resolution versus nominal resolution list versus sensitivity, specificity comments, and the limit also when you guys can tell us even more so, like with patients, then now when we get to patient translational application, now time becomes an issue, right? So for us, when we're trying to optimize sequences and get to the best images that we can with as close as possible to nominal resolution as we can, we don't have a limit, or we are less limited by time. We can keep people in the scanner for a long time. There are people that know how to be, what to be a subject means. They know how not to move, and so forth. And so it becomes a lot easier for us. But then when we move to translational application, now there's like limits in how still the patient is, how willing to coordinate, and how able he is to coordinate and keep attention. So I think now it's definitely resolution, but SNR also becomes an issue. So it goes back to the to the question of like how to best acquire data, maybe, bold versus vaso, specificity versus sensitivity. We need resolution, sure, nominal or functional, whatever. We need to understand the limits between the coupling for sure. But also like SNR becomes really important, because now the time, like what Renzo was saying, and what Lavinia was asking about whether we can do this at 3T versus 17, now SNR becomes an issue, because if the limit is time, then in 20 minutes, half an hour, when I get to 0.7, 0.6, are the data reliable enough to get subject? And then like funding, okay, maybe we can do it over several days, averaging over several days, get the subject back, test, retest, but then now it becomes expensive. So I don't know, there's lots of like different implications when we move to the translational application. And it's great to see what you guys are doing, but the things that we need to consider maybe with a slightly different way as when we're doing validation studies or something like that. It was more.
Yeah, the translational applications are precisely where I'm circling. And for that reason, in later years, even though I did do experimental fMRI as well, I'm more or less focused primarily on resting state, precisely for the time constraints. And it has its limitations, sure, but yeah, I'm trying to solve some problems. I might not be able to solve all of them. So I was wondering if maybe with layer fMRI and resting state, there might be something to fine tune our findings and maybe take it a step further towards clinical application. So precisely what I'm interested in is sensory processing in differential diagnosis, in autism and schizophrenia. And the way I go about it is a bit computationally, because we use non-invasive methods. So I'm looking at it using the Hurst exponent to estimate excitation inhibition ratio in different areas, depending on the parcellation. But I was wondering if maybe I could get more higher, perhaps, specificity with doing this kind of thing on their fMRI data.
Yeah, I think that there are certainly opportunities there and a lot of expertise around. Do any of the speakers have comments on this? Go ahead, Camille.
I wanted to make a comment about this question that was raised about, can I do this at 3 Tesla? And Renza pointed out that, of course, there are increasingly 3 Tesla studies aimed at layer fMRI. And especially, for example, with the denoising of fMRI signals that came about, which then improves the effective signal-to-noise measurement of an fMRI. I mean, there's quite a lot of interest, as Renzo also pointed out, that, can we do this at 3 Tesla? I want to point out that you have to be careful. It is not just signal-to-noise issue here. So you can have enough signal-to-noise, let's say by using denoising, or you use, for example, very long acquisitions so that you can get the resolution. But the contrast will also be field dependent, depending on what kind of contrast mechanism you are using. For example, if you are doing bold, gradient echo bold, which most of fMRI people are employing, and then gradient echo bold is not the same at 7 Tesla and at 3 Tesla. For example, at 3 Tesla, about 50% of the signal, this is a very old paper by David Norris's group, is coming from blood and intracellular blood, which is not very highly specific. And this is not the case at 7 Tesla. If you're doing vaso, for example, that may be very different. Vaso may be, okay, it has a lower signal to noise, but it may not be so sensitive. And if you can get infinite amount of SNR at 3 Tesla and 7 Tesla, maybe the vaso fMRI will look very similar, but gradient echo bold will not look similar. And it will not be very specific, if you like, at 3 Tesla to the layers.
Yeah, that's
Thank
very
you.
true.
I will use this to push for funding over here.
So we have a question in the chat, and this question is for June. So I believe this is asking about the paradigm in which people were shown different pictures, and they're asking, considering the TR is 3.5 seconds, is there anything that we really need to pay attention to when we design paradigms in light of Nyquist criteria? For example, any constraints on jittering or event onset times, etc.
Yeah, we did not 3.5, 3 second TR. That was at the at the moment that was the best we could achieve. But now we can actually do a lot faster, with the updated system on our site. So we went down to 2 seconds, I think 2.5. Depending on the coverage, you can go below 2 seconds as well. So you can certainly do jittering. There's no other things that's different from. So the only thing with the T2 prep method is that you have to align the start of a simulation with the preparation module, because that's when the contrast is generated. Slightly different from the EPI based method. That's the only difference, but otherwise it's the same.
Can I ask June? Hi, June. Why did in your preparation you use 2 180-degree pulses as opposed to a single 180-degree pulse?
Right.
What was the reason for that?
Yeah, so based on my understanding, that because there's always imperfection, so if we use 2, it's sort of a self-correcting. Although the downside is that you increase the SAR a lot as well. But eventually we tested both single and a double, and you saw the double seem to give us better images in general.
And then your after the T2 prep, then essentially your readout is still EPI, but with a very short TE. Is that what it was? I didn't quite. I mean,
no, it's the it didn't go into the detail. That's the 3D fast GRE readout, similar to MP Rage.
Okay, yeah.
Right.
So I wanted to, unless Luca has a comment, come back to you had this kind of discussion about layer fMRI as gaining kind of confidence in our measurements. I thought that that was particularly interesting and really applies to almost all of the studies that we typically look at. Obviously, at the same time, in all three of the talks that we heard today, there are not just acquisition choices that we make, but also analytical choices as we go through different things. How do you kind of see the relatively complicated process of getting a layer fMRI result and being able to trust that? And do you think we're headed towards kind of a standardized set of practices, or do you think that there are a whole bunch of different things that are really helpful for different questions and going different directions? Yeah.
I don't think I'm the best person to answer this question about to what extent we're moving towards kind of agreed upon layer fMRI pipelines, but I think to say the obvious, I think, I mean, ultimately it will be, I think, very important to cut the arbitrariness of some of our analysis choices and see whether we can move towards kind of standardized layer imaging pipelines, because yeah, I mean, these arbitrary decisions might change the way that our results look, and that will have to be moved out of the way before these things can become clinically useful. So that's not a very insightful answer, but maybe somebody who is closer to developing standardized pipelines can give a more insightful answer.
I think it leads very well into a question that we have in the chat from Natalia, which is, how far away are we from convincing clinicians to use layer fMRI in, and I'll extend her question just slightly, in clinical research or even in diagnosis?
I mean, I would potentially say it comes back a lot to the phenomena that one can show are layer specific. So really precisely explaining in principle which features can only be detected by certain kinds of layer specific analysis. And I think sort of some fields are moving in this direction. I think epilepsy is a field where there's a lot going on, I think, because small lesions in epilepsy, but also in MS, for instance, where clinicians are more and more, I think, convinced or also see in the data that certain small cortical lesions, for instance, can only be detected, or also the affected circuits can only be described, let's say, by using layer-specific MRI. I think also what I showed that, for example, cortical thickness as a major tool, also of clinicians as a readout to describe, for instance, neurodegeneration or across average functional readouts, when one can really provide the evidence, you know, that in principle this is not reflecting the disease profile, which, for example, is has been shown in epilepsy, for instance, that small lesions very much relate also to the kind of symptoms people show. That in principle there's a lot of dissociations between neurodegenerative profiles and the phenotype. I think in those situations where there's clear dissociations between the clinical profile and the brain profile, in those situations, I think that there's the, let's say, the motivation. The problem then is that, of course, when a clinical institute is going in this direction, they often just look at the data in principle. So there's a lot of studies just more kind of providing a clinician looking at high resolution data without any like quantification or standardization. So it's merely a description, let's say, of what you see in a single patient. And then this is, I think, more and more common, but then of course it comes to, it's hard to replicate. It's a little bit hard to say what they really saw because it's often just a description. So I think the next step would then be at least to take those clinical studies that exist in phenomena where we clearly see that it has a benefit, and to develop pipelines that can be used by clinicians. And this is, I think, something that for many cases, the pipelines are still too complicated. They take too long, so that it's sometimes hard to convince them, really the clinical people, to use them. Usually they do it in collaboration then with a basic science lab, which, I guess is not, in the long run, not what we want. I guess we want that the clinical scientists do it themselves. So I think it's a lot on also the people who develop the pipelines to trying to make them simpler and simpler, so that
Absolutely.
I can convince my collaboration partners also to use them, rather than that I do it for them always.
Yeah, it's interesting. I've heard of some sites trying to push this forward with the kind of increased usage of 70. It was like giving clinicians the 3T example that they normally have access to, but then in addition, giving a 70 scan along with it to try to kind of aid in, well, what's the extra information that you actually get and what can you make of it?
So as you're saying, like for you, the main limit is the feasibility of this application. So making it like, you know, rendering these applications standardized enough and useful time for clinicians to, you know, so it's practical.
Definitely. I think that the clinicians, specifically those working in neurology, for instance, have a lot of interest in using those data, because they have the patients and they don't see the phenotype in the brain. So for instance, in epilepsy, it's very obvious. They just don't find the lesion, right? And if you find the lesion, you can operate it. So I think there's a strong interest from the neurology side, I can definitely say. But very often then those data are acquired by, for example, Assistenzärzte in German, so the assistant doctors, and then they never properly analyzed. So they just die somewhere in the database, because at that point then, where you have somebody working part-time in the clinic and part-time in science, there you actually need you need some kind of quick application tools, and it's not that easy at the moment. So right, you have to try different routes sometimes with the data. It's not a kind of
but that's paradoxical. Still, I agree, it's not easy, but that's easier than convincing them as the validation, like what we're seeing is actually a layer signal and so forth. So if you think that the problem is making them usable in short amount of time and in a relatively like routine way, I think that we can get there. If instead we're talking about like how the old story of like how the real neuronal signal from layers, how do you validate it, and what you do in your work is beautiful when you're comparing it to mice models and so forth is great and convincing to a point, because then the mice brain is obviously different than the human brain, and so there's still a little bit of a disconnect. So it's great to hear that you think that the main limit, great on quotes, that the main limit is like making them like usable on a day-to-day like routine scanner, as opposed to convincing them of the veridicity of the effects.
I think neurology, they clearly see the dissociation in those. I think MS, epilepsy are very good examples, but also aging, neurodegeneration. You just see the dissociation between the phenotype of the patient and the brain marker, and very often they even exactly know what they're looking for. But then it's more on the hard side to realize this in a clinical project, I think. I think. That would be my perspective, at least, on this.
Yeah, I mean, to the extent that applies to psychiatry, I think the extent to which layer fMRI can contribute to the actual well-being of people with psychiatric conditions, I think, is tied to the extent that layer fMRI can pick up meaningful individual differences that ties into treatment directly. So I think one of the hurdles that psychiatry is running into is that a lot of illnesses that are probably very heterogeneous in origin are treated as a single entity. Whereas probably people with psychosis, it might be a multiple number of disorders that people have hallucinations probably for different reasons. I think ultimately, as I said, the degree to which layer fMRI can contribute to improving the well-being of these individuals is tied to the extent that can you pick up meaningful differences between these people that relate to a particular treatment. So if somebody has upregulation of superficial ASL, so maybe they respond better to a cholinergic drug, or perhaps people who have a increased influence of deep layer activity, maybe they'll be better treated with a serotonergic blocker or whatever. That's the type of thing that I think layer fMRI could potentially contribute to. And not necessarily have to be implemented on a per subject basis, but if we just understand that a particular phenomenology in psychosis, a particular type of hallucination is tied to a particular amyloid profile, that might help us perhaps to look at different treatment targets in future.
You do the other one. Sorry, I jump in because I can never find the hand to raise for some reason or to
You're
clap.
perfect, Natalia.
So, but can you actually use particular patient groups that have a particular treatment and try to if you start with a hypothesis on what the treatment might do and then try to examine it with laminar fMRI and see if you indeed find this effect, would that be helpful? So instead of trying to prove that there is something going on, because I can guess that clinicians may be a little bit skeptical, try to use a particular patient group with a particular either treatment or a very, very clearly defined disease condition to actually show that you can pick up this effect as a starting point, I mean.
Yeah, absolutely. I think that is the way to go. Perhaps to do comparative studies, but people with Parkinson's disease, visual hallucinations, and people with psychosis, and show that these might represent distinct layer-specific profiles, or even perhaps pharmacologically manipulate these layers and see whether you get distinct phenology and distinct layer profiles. It might just be a stepping stone of moving towards this kind of more precision psychiatric approach to these illnesses.
Yeah.
We have another question from the chat, and this is for Esther. It says, have you seen some T2 signal drop in the middle layers if you check MP2 range images, especially more significant signal drop in older adults? And then there's a second part, assuming that you collect T2 weighted images along with yours.
The T2 weighted, we didn't specify, I didn't have a T2 weighted sequence in the protocol. It was that it would have been great to add it actually, but it was already relatively long for our older adult sample. So we focused on the negative QSM, positive QSM as a marker for iron, but did not specifically actually look for, why was this, what kind of marker would this be? Perhaps to
Steve, if you're able to turn on your microphone.
What was the background of the question, perhaps?
Yeah, so actually, thank you for your answer. Actually, in my study, I can see some signal drop in the middle layer when you see the anatomic image of T2 star, T2 weighted image. Especially, there are some, background research, Gennady line. You can see the, middle layer is the fibers and signal drop. I just wonder if you can see the T2 weighted image and you can see some clear black line, some dark area in the middle line. Yeah, I just wonder.
Yeah, didn't focus on it, but you didn't have an age-related change in your data, right, on this marker, or because it would be interesting.
Sorry?
You didn't have an age-related change in this marker, right? Because that would be interesting. Yeah, no, we didn't focus on this. I think it would be interesting to look at it because there was a separate study where we actually specifically compared the T2 weighted with the MP2 range and the QSM marker on the cortical myelination. And there's some interesting dissociations also when it comes to layer-specific myelination between the two that we didn't so far go into much detail. But I agree that it would be great. It would be interesting to look at this in the context of aging. Yeah.
Thank you.
And then we also have a question from Fraser Eichen. This is also for Esther. We have ethical clearance to carry out laminar fMRI on children with GGE photosensitive epilepsy and children with FCD. Very interesting that your results indicate deep layers thinning and reduction of PARV cells in older people, as lots of data indicates most seizures on cortical organ initiate in deep layers.
Yeah, exactly. This was a little bit what I was indicating before, that in principle, it's exactly those clinical phenotypes where you actually expect the layer-specific, let's say, seizure origins. But so far, you couldn't really basically find a readout to quantify it. And I fully agree that I think in the case of epilepsy, it would be very interesting to combine it with fMRI. because it is very much expected that it's not only the cortical profile that shows the sensitivity, but specifically also actually the associated network change. And specifically because you have also forms of epilepsy where you expect more the superficial layers to be affected more. So it is, I think, a very interesting model system to look at this. And at the moment, we are designing also a paradigm where we think about and discuss what could be a good combination between structural and functional layer-specific markers in epilepsy to enhance detection, but also understand a little bit more the associated circuit. So I would be happy to talk perhaps further about it. So we are at the moment also working on this, let's say.
Yeah, that's really interesting, Esther. Perhaps we could check in about that in the future. We have some ideas, and we basically there's lots of animal work and recent LFP work in humans that indicates that both GGE, absent seizures, and also FCDs they initiate in deep layers. So we're designing experiments to try and, under the proviso that these layers are hyperexcitable, and so we will get some difference in the laminar profile. We've sort of stayed away from getting into the mechanistic side, where we're just looking for like a marker of, say, where an SCD is very subtle. What we plan to do is test some children where we know they have hyperexcitability, say in visual cortex with the photosensitivity. And then if we can isolate sort of a deep layer profile in the bulb, because of course it's not given that the bulb signal is going to match with animal or local field potential. And then we want to try and use this in a connectivity analysis to look for the FCDs where they don't show up on PET, or they're very subtle or invisible on MRI, basically. So it's really interesting that you know, obviously with the aging as well, with the link with aging in epilepsy, that you've also found deep layer thinning, a potential mechanism there. So yeah, really interesting.
Yeah, I also think that not only epilepsy, but in general, I think it's important that we also step a little bit towards having structural and functional layer-specific markers together. Because I think only having the function only having the structure, where I think many people just trying to develop some models or, you know, like detection algorithm to detect like the associated structural changes, they are often just not precise enough, because you could also have structure variations by other reasons. Whereas also only fMRI may sometimes be difficult to rely on totally. I think that the combination, you know, between the structural characterization and the functional readout may be most sensitive. However, I realized that, and coming back to the pipelines we have or we don't have, we actually don't have really good pipelines at the moment, where how one could, you know, reasonably combine those two data sets. So it's, let's say, challenging, coming, for example, to the question of how you align the data of different people in a way that you can compare the readouts meaningfully. Because of the strongly different myeloarchitectonics between people. So how could you develop a way to actually, for example, weight the functional readout based on the structure, or, you know, to take into account some of the variations you see in the data already, which targets a lot of the questions also on intersubject alignment and taking into account the microstructure, the cortical microstructure into this. So I think there's a lot of question to discuss when one thinks about a good paradigm, and but I think it's very fascinating and definitely the next step to go.
Yeah, definitely agree. Yeah, we will probably have all the children we will scan will probably have PET and MRI, 3T and 7T. So we have some form of comparison, at least, to sort of give us some validation of the findings from the lamina. What we'll end up is having a lot of PET positive but MRI negative. So I would imagine one thing it could be, just thinking off the top of my head, is to validate the PET, to sort of refine the PET. But we'll see. We've still got a long way to go. We've scanned some people on another ethics, some children with FCDs, and initial data looks like there is some slight difference in connectivity, but it's very early, and I wouldn't like to read too much into that.
But I agree that I think it may be most easy sometimes to start with a phenotype that is already there, and to go from there to the phenotypes that are not visible, rather than directly trying with the very difficult ones. I think that's
Yeah, agreed.
That sounds like a very rich data set, though. I have a quick question for June. So a lot of your results really focused on what are, I would say, difficult brain regions to think about layer fMRI. I mean, you had examples of entorhinal as well as these results with the olfactory bulb. Do you kind of see the type of imaging that you're doing as fitting into that section of how we image the brain, or do you find complementary results from your scanning in areas like V1 or somatosensory and motor cortices, where a lot of the more kind of traditional acquisition schemes are being used for layer fMRI?
Yeah, thanks. I think in terms of methods, if you ask me, if you imaging those visual or motor region which does not suffer from this dropout artifacts, conventional methods is just fine. Probably even better, because you have a higher contrast, and also the vasal methods, which is fine. The T2 prep method or some other similar methods is really for those high dropout regions that have this problem. So.
Very good.
Maybe a quick follow-up on this, and it kind of like relates to both June and Esther, talking about the structural and functional combined and so forth. So maybe one of the main issues that people have, like electrophysiologists have, with us doing layer fMRI is that they're not real layers, they're cortical depths. How do you know in which layer you're at, and so forth, and using structural contrast like T2 contrast, T2 star contrast or something, to being able to identify different cell concentration, and then use that as like anatomical fiduciary to then segment the cortex into different layers, as opposed to the standard equivolume or equidistant approach, may be a way forward. Now, the issue becomes that as soon as you come out of V1, where you don't have like your stria, which is clearly different cell concentration dark, and you can use that. How do you know? And so going to both what Esther was saying, using the structural in conjunction with the functional, and also what June showed in the olfactory bulb, we can actually see different cell concentration. How do you know which layer is which? And do we have enough sensitivity even on the structural contrast, on the T2 contrast, to be able to differentiate across different layers, and use that to then segment our cortex into layers, and then look at the functional responses on this, like, T2 guided segmentation? Is that doable?
Yeah, thanks. I think it's gonna be difficult. What I can say is, especially for the olfactory bulb, now we're doing is we're getting a specimen as well. We just want to do histology and to validate if these actually correspond to the layers. I think if you ask me, that's probably the ultimate test, to validate that. We're still not sure yet. So I don't know, Esther, maybe you have different opinion on.
No, I think it's just you need the ex vivo models, I guess, to then actually trying to validate them. And I think for some areas we have at least some basic models for motor cortex, sensory cortex, hippocampus, like those areas where actually people did ex vivo in vivo validations already. So at least there you have some models that you can use, let's say, to get an approximation. But there's also areas where we don't have this information, let's say. So you basically so in principle, I guess it's major work first for the ex vivo in vivo imaging to get such at least a model for the full cortex. And I think when you have at least the model, then you can also with your data actually trying to use it. So I guess it's definitely feasible, I would say, at least for first approximation. But the data is not yet there, let's say. Yeah, that's why I guess many people just focus on the primary areas at the moment, because there you have some validated work to work with, let's say.
This
I
is
have to
us
go
coming.
now. Sorry for
Yeah.
I have another meeting at 4. So thanks very much for the invite. I really enjoyed this, and I'm sure I'll see you guys soon.
Thank you for joining. And just in general, we are to the end of the hour anyway. So I would like to thank all of our speakers immensely for coming and showing us their work, and thank you everyone for the participation in discussions and questions. This was a really great session. Thank you.